see, or you are 4, I think you were 6. So let's wait maybe some minutes. Meanwhile, are there questions about the Hahn-Banach theorem that you would like to ask?
Professor, I have a question.
Yep.
So in the proof of Fenkel-Morel, I missed the last class because I had to go to the immigration office and I was looking through the book, and I don't understand one part.
Okay, so the Fenkel-Morel is the fact that the double transform is equal to itself.
Yes.
Okay.
In the proof, there's one part where it says that let epsilon greater than 0, since phi is
Positive.
at least, yeah, it's a positive, non-negative. So we have, hence by 14, we have this inequality.
Yeah.
So why are we choosing, why do we have to fix some epsilon here? I don't understand that, because by 14, I think since phi of x lies in the epigraph of phi, shouldn't we get the inequality just like that? Shouldn't we get like a strict inequality?
No, it's because you have that. So the thing was we arrived at this thing. So it was f bar of x bar. So the chosen, f bar and alpha bar is the chosen one which separates the epigraph from this point. No.
Yes.
Okay, so what you get is that plus alpha phi star star x bar less than beta less than f x bar plus alpha bar lambda for all lambda. Well, it doesn't matter because, for all lambda greater or equal than phi of x bar. Okay, the only problem is when you are not saying that x bar belongs to the domain of phi. You're not saying this.
Oh, I see.
You see what's the problem. So in your drawing may happen something like this, and it is still fine.
Okay. Thank you, Professor.
So if this happens, okay, the epsilon just plays the role that, well, this is positive, so I just can change a little bit the slope, and it's still fine.
Yes.
Okay. Okay, so now now we should. I told you that we have the proof. We should give the proof of the theorem. Let me cancel here because I'm thinking to skip for now this theorem, the proof, because the thing is very similar to the approach here, and but it takes some time, and I prefer to arrive to compact operators, that is very important. This is very important. There's a lot of applications, but okay, you can see the proof and when you need. But so let me just write the theorem so you don't forget it. So it's a dual. So you have to minimize one problem, then you minimize you maximize the other one. So or minimize the dual. Doesn't matter. You decide which side. So now they are convex. And then you assume that there exists x0 in the domain. So both are finite in x0, and one is continuous. Then, okay, the duality is that, well, the primal problem is equal to the max of a dual problem. So the continuous one is minus minus f star, sorry, psi star of f. Okay, and maybe instead of this, I suggest you some exercise. For example, is to prove, just to see how it's flexible. The distance, so let's say that K is convex. Then the distance from of x0 from K is equal to the max for f less or equal than 1 of the value in x0 minus the dual function of the indicator function of K. So this is the dual, so it's Legendre transform of this guy. Okay, and this thing is by definition the infimum which is written like the infimum of okay. So you see that, I mean, the fact that I can write that compute the distance. So the meaning of this guy is essentially, well, you take the f, the direction, such that it sees x0 at the maximal distance. Okay, so if you have k and I give you x0, how to find the distance? Well, in finite dimensional space, essentially you take this guy is more or less normal to the set k. Okay, here you cannot work with normality. We are not in a Hilbert space. I mean, the space is just normed. Well, however, you can rewrite the statement. And if you look at the formulation here and look at the formulation here, well, you observe that is exactly this formulation. So I decided to skip this theorem to the proof at least. And, but it is important not to know the proof, but it is important to use it. There are many examples where you rewrite objects as a sum of two convex functions, and then you can apply the statement. But very important is this condition here. One should not forget about these conditions. Otherwise, you get, of course, contradictions. Okay, so let's jump to something more interesting, I think. So, so today we are going to, so the Hahn-Banach and then the Banach-Steinhaus theorem and then the Grosset graph theorem are the cornerstones of linear analysis or linear functional analysis. So we are going to see the other two theorems. So today we're going to do the uniform boundedness theorem. So uniform boundedness. Boundedness, sorry. And open mapping. And then closed graph. So the idea of all this statement, I will sum up into saying the following. So if f from E to F is linear, okay, then, okay, some weaker condition implies well, boundedness, or continuity, or whatever. So essentially, all these statements tells you that some weak condition will imply a strong condition. So, but very important is that, of course, they do not hold for every map. The important thing is that this map should be linear. Okay. So the cornerstone of all this analysis is Baire category. Sorry, I forgot to say that, but these sets are Banach. They should be complete. And this is another important thing. Linear in vector spaces which are complete. So Baire category theorem. Okay, there are a lot of versions because at some point you can say what is a Baire space is a space where so this is a comment by myself. So at the end you use the statement that I'm giving you to define what is a Baire space, and then the corollary is a complete metric space is a Baire space. But here we are not doing topology, so we just say the theorem. So a complete X is complete metric space. I think you already seen it in real analysis. And Xn is a countable family of closed sets with non-empty interior, with empty interior. Then the interior of their union is empty. Or you can state the opposite fact, the countable intersection of everywhere dense open sets is dense. Okay, so I don't know if you like to have the proof, or you know already the statement, and then we skip the proof. This is up to you, because if anybody doesn't remember or prefers to see the proof, so this theorem is very deep, because it tells you something very deep about complete metric spaces.
We would like to see the proof.
You would like the proof? Well, okay, yes, so I have to work less. Because if you go too fast, I have to work more. Okay, so let's see the proof. I know at least another proof, but okay, this one is the classical one. Okay, so what I have to prove? I have to prove that, okay, the complement of this set that for all, so if I fix a ball, there exists a point y belonging to this ball such that y does not belong to what? To the union of Xn. Because otherwise, if I have a full ball inside the union, then the interior contains this ball. Okay, so now okay, so let's do graphically, because I think the theorem is pretty graphical. Okay, so step one. So I fix it. Let O1 is x minus x1, which is open and dense, because the interior of x1 is empty. So which means that, so I have fixed this ball which is B x0 R0. And then, well, I can pick another ball, which I can say it is closed. So I take a ball, which is B x1 R1 contained in O1. Because, okay, there exists for sure an open ball. I can take something smaller, no? And then the closure is inside O1. So this should be O1, for example. And then I have a smaller ball who contains the closure. Very well. So now repeat for the same. So step 2. So now I'm looking inside the ball B1. So left x minus 2, which is empty interior. So I deduce and dense. So this one is empty interior, so I get that with the same reasoning there exists, let's say, B x2 R2, which is contained in B x1 R1 intersection O2.
Professor.
Yep.
We have to put some condition for R2.
Yeah, sorry, I forgot. Yes, at the end it will come up. At the end I will discuss, because I have to prove it as Cauchy sequence. Yes, okay, I can say here that R1 is less than R0 half. And here I can take R2 is less than R1 half, or let's say, so it is less than R0 divided by 4. Okay, so let's go back to the drawing. So what I did here, there is another ball which has half the radius and is inside. So if I go on, a step n, so there exists a ball xn Rn contained in the ball xn minus 1 Rn minus 1 On, and Rn less than, okay, doesn't matter. What's important is Rn minus 1 over 2. Let's write it this way, less than R0 2 to the minus n. Okay? So we consider now xn. So consider the sequence of the centers. Okay, so we start here with my x0. Then I have my x1. Then x2, and then I'll go on. Okay, if you observe the distance, then we have the norm of xn minus 1.
No, matrix. We have not norm.
Pardon?
Matrix space, not norm space.
Yeah, sorry. This happens when you know the proof by heart, and then you don't care too much. Less than, okay, 2 to the minus n R0. So it means that it is Cauchy. Now, being complete, so xn converges to some x. And now let's look. So xn converges to some x, so xn bx, the limit, belongs to each closed ball being closed. So x belongs, which is contained in On. So x belongs to the intersection of On, which is what we wanted to prove. So this x is our y. Very well. So, now with this theorem, we start with uniform boundedness. Okay. Since I'm using bare category, the spaces are needed to be vector space, normed space complete. So E and F are Banach spaces.
Professor, I think if does not, we can generalize these conditions. If does not require Banach space.
No.
Enough.
Does not.
Yeah, be Banach space. What I'm saying?
Okay, yes. In the statement,
The condition.
well, yeah, because the condition, okay, let's see, the condition is on the space X. But okay, in the statement, I take both Banach. But clearly, the condition is in the space X because you say when it is larger, so you don't need to have F Banach. But okay.
In the proof, we don't need.
No, you don't need the statement is on the space X. But okay, I think it's okay. And then we have Ti, with I is some index, is a family of linear operators. Bounded linear operators. So bounded means with respect to, oh sorry, this is a family of linear operators. So linear operators, not bound. No, sorry, because I'm taking different, yeah, bound. Say, I don't like how it is written here, because I didn't introduce the norm of continuous linear operators. So I should say in which sense let me see, because here I'm taking okay, okay, which means in some sense let me see, because I don't like the way that is written here. Okay. So I'm skipping a little bit, but let me give. So this means essentially that I define, so indeed, sorry, I don't like the way it's written. I'm sorry. I took a road, but then I don't like this one. So let E and F normed space. So we define the space, the linear continuous operator over F. So these are linear and continuous operators. And they are defined by the following. From E to F with the norm. This is the normed space. Norm of Tx, norm of T, sorry, is the supremum. Norm of X equal to 1, norm of Tx. So a priori, we don't know if all linear continuous operators, they satisfy this supremum. But okay, we give for granted. So this is the definition of the set of linear operators which satisfies this uniform bound. That's it. Okay, now we give the theorem. Steinhaus. So let E and F Banach and Ti I is some family, a family of continuous bounded operators, of bounded operators. These are called something bounded. Instead of continuous are bounded. Simply because they reflect this bounded. In the family of linear operators. Now, the uniform bounded theorem is because you have assumed a pointwise bound. So for all x in E, the supremum of the norm Tix is less than plus infinity. Then we have a uniform bound. So the supreme, so which means that the supremum over I of the norm is less than plus infinity. So this is when I fix x, and this on the other hand, x is free to run across all vector of norm 1. So it's something like, suppose that I have a pointwise estimate, then what I get is a uniform Lipschitz estimate, because this is the slope. Okay? Clearly, this cannot be true for any continuous functions. And the role is really, what plays the role is the linearity. So well, this is true. It's not true. Okay, let's keep. Because then I'm okay. Here I keep because we use the Baer theorem. So proof of Banach-Steinhaus. Okay, so now we define some set. So define xn equal to the set. Okay, so this is uniformly bounded, no? Which means that if I define as the point x such that the norm of Tix is less than n, okay, let's look at this guy. So this guy is closed. It's closed because Ti is continuous. Ti is continuous, and the norm is clearly continuous. Norm of f is continuous on f. Okay, so it is the inverse with respect to a continuous function of closed set. It's closed. And now the intersection, so I deduce xn is closed. Okay, so here I use the continuity assumption. Now I need to use the pointwise condition. The pointwise condition is that since the supremum is bounded, every point belongs to the union. So the pointwise bound gives that E is the union of on n or all xn. So E is a union of closed sets. Countable union of closed set.
Professor, in the definition of the set, not m, n in the brackets, in the definition of x, n. Not m, n in the bracket.
In the bracket, which bracket?
Definition of x, n.
Xn is the
Yes.
intersection over I of
Yes, yes.
x where
Not m, n.
n,
M.
this is n.
N. Ah, sorry. It's
No
n.
problem. It's is n. Xn. You fix n, so which is an integer, and you take all the points such that all I is bound. It's okay, no?
Okay, just I am confusing with m and n.
Yeah, it's my fault. I don't know. You prefer to have some. Okay, let's say this is n, and this is n. Is better now, and now this is n, and this is n. Is it better now? Okay, and then let's go. This is n2. Is okay?
Okay, thank you.
Sorry. Okay, so this guy Bear implies that at least one S-donut interior. There exists, let's say, N0 such that the interior of X N0 is not empty. Okay, so, well, this reads, so let's go back to N0. So it means that there exists. So in the interior, this contains some ball. And so the image of X0 plus R0Z with Z less than 1, okay, is less than N0. Because exactly it tells me that in this ball, the supremum is less than N0, so I get that for all Ti, this guy holds. Okay, and then I just apply, well, the triangle property of the norm. So what I get is that the norm of Ti R 0Z, okay, let me put the bilinearity. Minus the norm of Ti X0. So what I get is that Ti Z F less or equal, okay, this guy is again in size, so it's less than 2 and 0. Bar R. And this is my thing down there. Okay? Okay, now let's see the applications. See that that linearity plays a huge role in the last step. Otherwise, what you get is that there exists something where it is uniformly bounded. But you don't get that, it is Lipschitz. A corollary. Like this one, doesn't matter. Okay. If Tn is a sequence of bounded operator converging pointwise to T, which means that Tn x, the limit over n for all x fixed, is equal to T for all x in E fixed. So I'm taking the limit for pointwise. Then, okay. So they are uniformly bounded. The limit is a bounded operator. And actually, and the norm of T is the lim-inf of the norm of Tn. Okay, so it is lower semi-continuous. Proof, there is not much to be done here because it's exactly this theorem plus the definition of norm. So let's see. So let's say Banach-Steinhaus, well, okay, it is a family of bounded linear operators, certainly, and it is pointwise bounded simply because if the limit exists, should be bound in R. Okay, so I deduce immediately that the norm is uniformly bounded. So the first point directly from Banach-Steinhaus. So the second point, that it is linear. Okay, let's see, I do it. Well, okay, it is bounded set. Well, now, norm of Tx okay, so let's compute. This is the limit. The norm is continuous. And this is now, I observe now that I have that their supremum is uniformly bounded, so it's less or equal than, okay. Now, since I do the inequality, I shall put lim-inf. This is because norm of T and x less or equal than norm of Tn norm of x. So if I take the limits of the lim-inf on both sides, this guy is convergent to this guy, and then I'm left with this guy. Okay, so it's less or equal than the supremum. Which tells me that it's certainly bounded by the point 1, and then I get from this inequality that this guy over here, so this norm is less than this guy over here, by definition of norm, no? Because norm of T is sup over norm of x equal to 1, norm of dx. Okay. So we are left with, well, nothing. And now we start with the things which are more interesting. Now I can cancel this guy. Another corollary. Okay, maybe I forget to say things, but okay, maybe you can lower the assumption on the arrival space, but since we want to have something which holds everywhere, and in this chapter, the sets are Banach, so complete. So let B contained in E Banach. Whenever I forget, it would be Banach, such that f of B is bounded in R for all f in E star. So what we call is, so whenever I test with one of my linear functional, I get a bounded set. Then B is bounded. So just to be clear, the difference in the statement. So the first one, f of B bounded, means that let's say, there exists, okay, some constant, well, the set, let's say, f of x, x in B, is bounded in R. Okay? So I'm not saying that, I'm just saying that whenever I look through a linear function, it is bounded. The other one, it says that B bounded, it means that the supremum of norm of x is less than plus infinity. And here we cannot use the Hahn-Banach theorem. Okay? Because one may suggest, okay, I have an x, a sequence of x which diverges. However, the functional f which which gives you the norm of that particular x depend on x. So you cannot, it doesn't work. Instead, it is a corollary of it is a corollary of this statement. Okay? So the proof. So I have to, in order to apply, well, Hahn-Banach, or let's say Hahn-Banach, so I have to define which are the sets and the linear operators. Okay. So here I'm applying something on the function. So I'm saying something about the boundedness of linear operator, which are my x. So x should be the linear operator on the space. And so the space will be the dual space E star. So we apply Banach-Steinhaus to the operator, linear operator from E star into R, given by, so to F I associate Fx belongs to my set B. So this is my family of linear operator. Just this is the thing. So now the statement, let's see. Well, Banach, this works. Clearly is bounded linear operators, certainly. And why it is pointwise bounded? Because, so this family, let's say it is called the family F of B. F of B is pointwise bounded, which is the assumption, because, well, because f of B is bounded. So the supremum over my family f of B of these operators, well, which is the notation is not very nice, is the supremum over B which is, by definition, is bounded in the arrival space, which is R. So I deduce. Okay, I deduce that there exists a uniform bound, which is given by, well, some constant, which I can compute. Or, well, I can compute. There exists some constant. So it means that the sup over family FB of the norm of this operator, let's say Tx, let's say these are Tx of F. Well, but the norm of Tx of F, I know that it is equal to the norm of X. Because I have Hahn-Banach theorem. You see, now I'm using really Hahn-Banach theorem. And so it is strongly bounded. usual statement. Let's see the notation. Okay. So now we, instead of having a set in E, we take a set in E star. Such that for all x, f, so the supremum over B star of fx is bounded in R. But I deduce the same stuff, so then B star is bounded. Okay. So let's do the proof and then some comment. Okay, the proof is the same, but for one part, which is, so the proof is the same, but in this passage. So here I need to use the Hahn-Banach theorem to say that the supremum over all f, so the norm of the linear operator is equal to the norm of x, while on the other hand, for when I'm in this statement, so let's go back. So let's jump. The proof is the same as before until what we get is the supremum over B star of f of the norm, well, of the linear operator. I'm just okay. Let's do the proof. I think I'm confusing you instead of doing. So the thing is before apply Banach-Steinhaus to to the linear operator of E with values in R, which is E star, no? So the statement tells me that, so for all x, I associate, let's say, f of x, which is fx. And this is my linear operator, tf, let's say, tf. Then I get the sup of the norm of these operators over f belonging to B star. But now the norm of this operator is by definition, while here is by Hahn-Banach. This is Hahn-Banach. And this is by definition, is the supremum. E star. Okay, this is what I wanted to point out, no? Is as we saw earlier, is just, okay. So done these two applications. Some comments. The comments is that it's these two corollaries are very important because they tell you that in order to have the boundedness, it is enough to check with respect to linear functional as in the finite dimensional space. And this is definitely a non-trivial situation. Okay, so now we take other two fundamental theorems, which well, plays an important role and have a lot of applications. So,
Professor, one comment again. In the second corollary,
yep.
we don't need the space being a Banach space. It's enough space, just normal space in the second corollary.
Yeah, because it's the space, the arrival space. Yeah, well, you need just the starting space, which is, So here we apply to E star, so you don't need that T is Banach. Yes?
No, in the previous one. The previous one, because we use in here E star.
Yes, sorry, yes, no, yeah, no, it's the starting space, which is, in this one, the
Yes,
linear
yes.
operator should act on a Banach space.
Yes, yes. Because we use E star. E star is always Banach space, so we can use Banach-Stenghaus theorem.
But where here?
Yes, yes, in this corollary.
Yes, because you need, yes, because E star is always a Banach. You don't need it to be Banach, yes. Because you apply to E star.
Yes, yes. So
Yeah. You have an Banach theorem and you have enough. Yeah, but I don't want to enter here. I mean, these are just, well, if you look at the proof, you see. So theorem, open mapping. Was not pink, was not red. Well, I click my red thing here. Open mapping. Okay, so E and F are Banach, and an operator, take an operator, bounded operator, which is how do I write it? Surjective. So the T, which means T of E is equal to F. Then there exists R, or how you write it? C, sorry. C such that the ball in F of radius C is contained in the image of the ball of radius 1. So this tells you the following. So it tells that the image of open sets is open. No? Because, okay, by translation, it being a linear operator, I'm saying that the image of any ball contains a smaller ball. So it is an open. It's an open set. And that's why the theorem, no? The name of the theorem is open mapping. So T, if T is surjective and bounded, is an open mapping. Okay, so let's start with the proof. I don't know if give you the proof or immediately give in the main application. Let's see immediately the application first. So corollary T from EF bijective. So which means that T is surjective. So there exists T to the minus 1, which certainly is linear, but I don't know if it is bound. Then T minus 1 is bounded. Because you see from this fact, so let's see subito, immediately the application. The proof is because from this guy, so the ball of radius C is contained in the image of the ball of radius 1. Well, this implies that the inverse of the ball of radius C is contained in the ball of radius 1. And so the norm is 1 over C, less or equal than 1 over C. By linearity, no? I divide by 1 over C. I divide by C, so 1, and then I get 1 over C. So let's do the proof now. Well, and actually, okay, let's do immediately also the second corollary, just for fun. So we don't need to come back. Corollary. That's E Banach. And with two norms. Norm 1 and norm 2. So I have two norms, and E is Banach with respect of both of them. Okay? Assume that one is stronger. So let's say norm 1 is less or equal than, okay, norm 2. Then there exists a constant such that norm 2 is less than a constant norm 1. So you cannot have, so if you have a bound, the two norms are equivalent. So this means that they are equivalent. Why is that so? Well, we can apply this thing here the previous corollary.
Identity, no?
Pardon?
Identity. Identity.
To identity. So identity you consider by mapping, let's say, the first space with the norm 1, the norm 2 to the same space with the norm 1, which is continuous because of the assumption. And so you get that the C will be the inverse of the norm that I get here. Very well. So now let's do the proof of this open mapping theorem. Okay. Okay, as usual, we define, well, we need to use Baire theorem. So we need to define some closed sets. So we would like to say that one of those open balls, so let's say that one is open, and what we would like to say? We would like to say that, let me put here. Okay, let's do this. We would like to say that the image of some ball centered to the origin contains an open set. But the thing is that, so what breaks the computation here is that certainly the union over n of these balls is equal to F because it is surjective, but they are not closed. So I cannot apply Baire directly to this ball, but I can apply to the closure, and then I'm fine with Baire. By Baire, I deduce that there exists, let's say, n0, and well, since it's open, just to see the notation, okay. and a ball okay. Because then I'm going to scale. Let's say x bar, r bar contained in the closure of the image of 0, n. Okay? But now I scale, because t is linear. So if I scale to 1 this guy, I just divide by n this guy. So I deduce that b x0 r0, where x is contained in t b0 n, and my choice would be that x0 is x bar over n, and r0 is r bar over n. N0, sorry, there exists a 0, N0. This is 1. So I divide by N0 by linearity. Okay, but then by linearity, so this guy is symmetric with respect to the origin and convex. Again, T linear. So the T of B01 closed is convex and symmetric with respect to the origin. Okay, which is not so trivial, because certainly this guy without the closure is symmetric and convex. And I'm saying that if you close a symmetric and convex set with a non-empty interior, well, you get something symmetric and convex. But okay, it's I think you can give me from granted. It's not that deep. So I deduce minus x0 r is contained in T B01 closed. Well, and now it is convex, so I deduce that the convex combination is contained, and the convex combination is clearly the ball centered in 0. So here are just some linear operations in order to deduce this fact. Okay, so the linearity is it's here. You see, from any open set, I can pass to a ball around 0. Now we have to conclude now that we have to remove this open here. So the second step remove the closure. Well, what we just proved is that so that y, which belongs to the ball of radius 0, and let's take half of this quantity. Okay? So being in the closure, then there exists from the notation here z z0. Such that, so I want to say that since it is inside my ball, there exists a point whose image is as close as I want. Okay, in particular, I can say that there exists a z0 such that y minus t z0 is less than, okay, r0 over 4. Okay, so now what I get? I get that this is a point whose distance is 0 over 4, so I can repeat. Okay, so I repeat the same statement. Then there exists z1, which belongs now, okay, sorry, let me think. So now I'm apply the same step to, let's call this y1. So the norm is half of this norm. Okay, and this I take 1/2, sorry, otherwise I don't get 1/2. So the norm is half of this norm, and so I can apply the same, and I get there exists Z1 now belongs to B0 1/4, simply because this guy has a norm which is half of this guy, and everything is linear, such that, so it should be y1 minus z1 minus tz1 is less than, well, as much as r0 over 8. So, and this means the norm of y, the original one, minus t0 plus z1 less than r0 over 8. Okay, so I proceed in this way. What I get, well, you understand that what I get is a Cauchy sequence, one converging to y and the other converging to another z. So at the step n, there exists Zn, which belongs to the ball 0, what is 2 to the minus n plus 1, n minus 1, such that y minus, okay, t z0 plus z1 plus zn, okay, is less than r0 divided by 2n plus 2. Okay, this is just the fact that I'm just using this observation and scale it accordingly to the needs. Okay, so let's see. So Zn is a Cauchy sequence. So the sum, actually sum over Zn up to n is Cauchy. Because you see the norm is divided in half, so it's clearly Cauchy. And so Zn, the sum over n, converges to some z, and being t continuous, the sum, or t of the sum, converges to tz. Okay, what is the norm of z? Well, the norm of z is less than 1, simply because each one has norm less than, so it is 1/2, then you have 1/4, then 1 or 2.
Inequality.
Get 1. Pardon?
Triangle, inequality.
No problem. So now the last one is this guy. So if you pass to the limit, so let's pass to limit, and then we obtain that y minus tz is equal to 0. So tz is equal to y. Okay, so this is the proof. And okay, we saw the corollary. Now the last theorem, because in this chapter we will jump, this is the last theorem of the second chapter. The other are a little bit more, I don't know if we are going to cover them, probably not. Orthogonality relation and unbounded operators, if there is time, but I don't think so. So open mapping, and then we change the name, closed graph. It's easy to remember because one is open, the other is closed. As usual, we take Banach. Okay. And T is a linear operator. Then T is bounded. Graph of T is closed. Okay, at this point this clarifies more or less why the notion of continuity is the notion of boundedness, no? At this point there is only one notion of continuity, which is the boundedness. Okay, so proof. Well, the graph of a continuous function is closed. This is a general fact. So let's say T continuous. So T, yes, is a bounded and continuous operator. Then graph T is closed. Really, by really the definition of continuity. It is just the definition. Okay, so we have the opposite. Conversely, define the norm of one, a new norm, which is the, well, this is a nice, is important notion, so let me say this is the graph norm. It's a very important here, but for continuous operator, it turns out to be equivalent. For unbounded operators, so non-continuous operator, instead, it turns out to be another norm, which is a good norm on the domain. So it's important, but here is just an application of this object. Okay, very often, as I said 2 days ago, I'm not writing which are the two norms when it is clear. And well, here I write just for definiteness, but clearly the norm of Tx is in F. And this guy is clearly greater or equal than norm of X. Okay? So now I'm saying that norm of 1 is a norm, making E Banach. Okay, this I leave a little bit as an exercise because it's fun. Just some comment. Well, the properties, the subadditivity and the linearity, they are clear. The positive and the homogeneity, they are clear. So the only thing is why E is Banach with respect to this norm. Any observation? So why Banach? I leave. Well, the suggestion is that we are not using the assumption. There is an assumption which tells me it is Banach. Okay. So then let's apply now this thing here. By corollary, that guy, there exists a constant C such that the norm 1 is less or equal than the constant C, the norm, the original norm. Okay, let's replace the stuff. So you get the norm of TF C minus 1 norm of X. Okay, which means it is bounded. Okay, so I think this is the end, and I know that starting from next week you have the tutorial. Actually, I don't have your email, but I give you mine. I gave you mine. So okay, I did not write which exercise I would suggest to you, but I'd write to the tutor. And okay, if there are no questions, I think I would like to start with, because otherwise we don't finish the program. Let's see.
Professor,
Yeah.
is it possible that you send the exercises to us as well so that we can think about it beforehand?
Yeah. Yes, but then I need to know that because I look a little bit at the exercise and I selected some, but I don't know. You want me to list them? I'm not so sure there, so I just have a fast look. Because, so the best thing is that since you have my email, you write me an email and I email you and the tutor the list of exercises which I consider interesting.
Okay, thank you.
This is the best. Otherwise, I can list, but I have to check a little bit more. I think if there are no other questions, we go on. So we start with the new subject. And this is the most important subject. That's why I want to arrive early of the course. Are there questions? I know that maybe it's a little bit heavy. I don't know. It's difficult to understand in this way. Okay, maybe let's do some exercise. I know that it is not the best way to change mind. Okay, let's do this exercise. Maybe we just for. So assume that T and X converge to Tx for all X fixed. Show that if Xn converges to X, Tn Xn converges to Tx. Okay. It's easy by uniform bounding principle. Because I know, so the hint of sketch is the following, is the norm of Tn. Okay, this is uniformly bounded. And then I just write the triangle inequality. Tn minus T. So Tn Xn minus X, Tn minus Tx. And then this guy is less than m, the difference in the norm. Okay, you see? This was easy. Okay, this is... Okay, the adjoint. Don't remember the number. Define, so let T the adjoint T star by, okay, let's say T star fx, or sorry, T star, I should put another one. Y, this is in the dual norm of x, let's say T star of f is equal to f, h applied to x is equal to h tx in E, in f, and this is in E. Incredible. So this T star show that star belongs to the linear functional from f star to E star. And actually, it's the same norm. Okay, these are just are elementary. So this is just something easy to see here. Then, okay, many exercises are about the part that we skipped, these unbounded operators, so I don't want to do that. Okay, so I prefer to introduce what is the main tool, we will see it around the beginning, the main part of the next lecture. And even if I repeat twice. So, starting from the next lecture, the key of the course are the weak topologies. So weak topologies are the topology generated by the functions, the family of functions x, fx, where f is in the dual. So this is the topology, is denoted by sigma E star. So essentially is the weakest topology which makes all these functions continuous. Well, now there is some general theory, and so for example, the base of open sets, so a base or pre-base, let's say a base of open sets is equal to, well, let's say, O, which depends, all the x such that fi x minus alpha I less than epsilon, where fi, so I is finite, 1 to n. Okay, these are general theory. I don't want to discuss it. We will see later. So the thing you see that these are just like some finite codimensional neighborhood of finite codimensional space. Okay? So what is the advantage of the topology with respect to the strong topology? Clearly, this topology is contained in the strong topology. Simply because all these functions are continuous for a strong topology. So all the needed open sets are inside the strong topology. And in general,
I think reverse, Professor. Final. Strict topology is content.
yeah, and it is infinite dimensional, yes. In infinite dimensional space, this topology is stricter than the topology, the strong topology. So why do we need some weak topology? Because being a weak topology, it has more compact sets. And so to have compact set is very important because if we know also that is metrizable, then we get subsequences converging. Well, another thing we can do is the following, is define okay, by the family of functions x maps to f maps to fx x varying in E. So this is defined as a sigma E star E. So is the topology inherited by E star, and it's called weak star topology. Okay, so in E star we have another topology, no? So we have that sigma, the weak star topology is contained in the weak topology, which is contained in the strong on E star. Okay? And the topologies are clearly non-equivalent unless it is, well, it is reflexive to our equivalent, otherwise they are not. Okay, so we are even happier here because this is a topology which is still even smaller, and so we still have more compact sets. In particular, we will see that the unit ball, which is non-compact in these topologies here, is compact. Okay, I think I stop here. If you write me an email, in order to let you to know your email address, I'll send you the list of exercises, not only from this book, also some other, because some of these exercises are not maybe focused exactly on the thing that I care. Are there questions? Okay. So we'll see you next Monday, and we will restart this subject in weak topologies, and this will take 2 or 3 lectures because it's very long. There are many important theorems here which we need to address.
Thank you, Professor.
Okay, have a good weekend.
Thank you.
Thank you.
Thank you.